Welcome to Lab 3, and this is the circuit experiment. So the purpose of this lab was to predict how a circuit will respond to resistors in parallel and series, and then to also observe and measure those currents. And the method to do this lab was done in a simulation that was online, and then I also used Google Sheets to graph some stuff. And then to identify the system is the circuit, and everything else is the surroundings. So for some quick results, the node and a loop rule were supported, and the current in an RC circuit had an exponential time dependence. And then we'll get into some of those numbers here later. So some quick physics principles. The node rule is the current flowing into the node must be equal to the current flowing out, and this shows that there is charge conservation. The loop rule is the sum of all the electric potential differences, and the loop is zero, so this shows that there's energy conservation. Ohm's rule is the current through conductor is directly proportional to the voltage. And then we also have Kirchhoff's laws, which help us get to both the node and the loop rule. So to predict the currents through 1 and 2, I predicted that the currents would be the same since they are in series, and this would result in them having 0.02 amps. So then I tested this in the simulation, and I also did the ammeter doing it straight first and then also flipping it. And we saw that our prediction was also correct, and that also nothing changes whenever we rotate that ammeter. So next I tested it by putting a voltage meter there, and the ammeter reads 0 amps. And this is just because the voltmeter has very high resistance. So it's not measuring any current at that location since there's such high resistance from the voltmeter, and then voltmeter reads 3 volts because there's no other voltage drop, so V is equal to IR. Now, for this part of the experiment, it was showing basically what the different potential differences were. So I did VB minus IR2 is equal to 0, and that's from the loop rule. And I found that the potential difference is +3, that's just from the 2 batteries. And then I also found the voltage between C and D, which would be the first resistor, is negative 0.96 volts. And then between E and F, which is the second resistor, it's negative 2.04 volts. And then the rest would just be 0 change because it's just straight and there's no resistance present. So there's nothing generating or basically resisting that current. Next, I wanted to show this little graph that basically shows how voltage changes throughout it. And I also said that the voltmeter is high resistance, so there's very little current flow. I also said in a total loop that the change of potential would be 0 because this is the loop rule, and this is also shown by the graph. So next, we put the ammeter in basically parallel to this resistor, and because the ammeter has extremely low resistance, the current is going to move through the ammeter as opposed to moving through that second resistor, which is why we see that they're both reading 0.06 amps. And this is also, we can calculate it and predict it with V minus IR, and we also will get 0.06 amps. So next is the resistance of each circuit element. So I went ahead and calculated all of that. So the resistance, I got 48, 102, the wire is 0. And this doesn't exactly match our simulation or what we expected to get, but that's okay because it's very close. So we can just kind of say this is rounding error. So next for the RC circuit, I determined basically what the ohms were per second and showed that like the charging versus discharging. And basically all this shows is that it's the same for charging and discharging. And then you can kind of see the setup. I put a little box around the connection to show like when it would be charging versus like when it's not charging. And then for the RC circuits, so I plotted this with my timer about the voltage and then also on the natural log plot to show that the 9-volt battery connected to the capacitor and then also the bulb. And the predicted RC VIOT is 6, but the actual one that I observed from my timer was 1 over the slope, which is equal to 6.85, which is still pretty close to the predicted one. So some sources of error is that we are using online simulations, and the simulation is oversimplified, so it doesn't really completely represent the real world because we do have some simplifications. I'll talk about that more on the next slide. And then also just human error. I'm kind of slow with starting and stopping the stopwatch, so there's definitely a little bit of a delay in like what the actual time is versus the observed time. So further discussion, if we had used an actual ammeter, then the resistance would be associated with the ammeter and it wouldn't just be 0 like we simplified it to in our simulation. It would still be extremely low though, but this would decrease the amount of total current we have in our circuit. And then what if we used a real battery and no resistor? With no resistor, you would assume that like a capacitor would instantaneously charge, and in the simulation, it would show this. But in the real world, like batteries do have an associated internal resistance, and also steady state is not something that is going to be instantaneous. So it would probably take a few milliseconds before the capacitor would charge up completely. And that's it. And thanks for watching my physics lab. Bye.